Moving on to the direction of lines. So, direction of lines is defined as the horizontal angle that it makes with a reference line. So, in other words, the horizontal angle that a line creates with a reference line determines its direction of line. There are various kinds of angles which can be used to describe the direction of line. Directions may be defined by means of interior and exterior angles, deflection angles, angle to the right, bearings, and azimuth. First, we have interior angle. So, interior angles are angles between adjacent lines in a closed polygon, meaning interior angles are the angles lying inside a closed traverse. So, interior angles may be measured clockwise or counterclockwise. Our first equation here is used to get the total degrees of any closed polygon. So, the summation of all angles is equal to n, where n is the total number of knots or angles inside the polygon, minus 2 times 180 degrees. Next, we have the equation used to get the total error. So, error is equals to n minus 2 times 180 degrees minus the summation of all angles. And lastly, we have the equation used to get the total correction needed to adjust the polygon. So, correction is equal to error over the number of knots. So, let's try to work an example on how to check if the given polygon is balanced and how to adjust each interior angle if it is not. So, here we have a closed polygon and this will be our plan view. The given information for the angles is as follows. So we have angle A, which is 108 degrees 25 minutes 4 seconds. Angle B, which is 139 degrees 14 minutes 27 seconds. Angle C, which is 88 degrees 40 minutes 27 seconds. Angle D, which is 110 seconds 51 minutes 36 seconds. And angle E, which is 92 degrees 22 minutes and 1 second. So first is we have to get the sum of all angles. So we just have to add all of this angle. So to add this, we need to use our scientific calculator. So this will be 539 degrees 59 seconds 35 minutes. So this is the summation of all angles. Next is we need to verify if the angles are balanced. So in order to do that, we need to find the total degrees for our given polygon using our first equation. So our first equation was the summation of all angles is equal to n, where n is the total number of knots or the angles, minus 2 times 180 degrees. So n, so we have here 5 angles or knots, so this will be 5 minus 2 times 180 degrees. So 3 times 180 degrees, this will be 540 degrees. So we notice that the summation of all angles is not equal to our total degrees. So we can say that the given polygon is not balanced. So to balance our polygon, we need first to determine our error. So how do we determine our error? So error is equals to the total degrees minus the summation of all angles. So our total degrees is 540 degrees minus this, because this is our summation of all angles, so this 539 degrees, 59 minutes and 35 seconds. Now use again your scientific calculator to calculate this, and this will give us 25 seconds. So this 25 seconds here is our error, and to adjust or to correct our angles here, to balance our polygon, we need to distribute 25 seconds here to the angles. So to get the correction needed to add in each angle, we have the formula correction is equal to the error divided by the total number of knots. So we have the error, which is 25, divided by the number of knots, so we have 5. This will give us 5 seconds, and this will be the correction needed that we will add in each interior angle to adjust them. So we have the angle A, 108 degrees, 25 minutes, 4 seconds, plus 5 seconds. This will give us 108 degrees, 25 minutes, and 9 seconds. For angle B, so we will just compute the remaining ones following the same procedure. So we have angle B, 139 degrees, 40 minutes, 27 seconds, plus 5 seconds. This will give us 139 degrees, 40 minutes, 32 minutes. Angle C, which is 88 degrees, 40 minutes, and 27 seconds, plus 5 seconds. This will give us 88 degrees, 40 minutes, 32 seconds. Angle D, which is 110 degrees, 51 minutes and 36 seconds. So plus 5 seconds. This will give us 110 degrees, 51 minutes and 41 seconds. Angle E, which is 92 degrees, 22 minutes and 1 second. So plus 5, this will give us 92 degrees, 22 minutes and 6 seconds. So in order to check if the given polygon is now balanced, we just had to add all of these angles. So use again your scientific calculator, and this will give us 540 degrees. 540 degrees. So there you have it. Our summation of all angles is now equal to our total degrees. So that means that our given polygon is now balanced. Next, we have the exterior angle. So exterior angles are angles located outside the closed polygon. So it is also referred to as experiments to interior angles. Note that each exterior angles is complementary to its interior angle. Now, With exterior angle, we can follow the same process to that of the interior angle. So first is we just have to determine if the given polygon is balanced or not. And the only difference relies on the fact that the equation for getting the total degrees changes slightly. So instead of subtracting 2 from the number of knots, we will add 2. And other than that, everything else remains the same. Next is we have the deflection angles. So deflection angles are angles between the line and the prolongation of the preceding line. So in other words, it is the angle between the extension of the preceding line to the next line. So it is also defined as the amount of angular deviate from a straight line to stay on course. So clockwise deflection is considered positive and counterclockwise is considered as negative. So let's try to look at an example. So we will start in a given example at the right. So to determine the deflection angle between lines AB and BC, line AB projected a line from the ending point, and that projected line will be parallel to line AB. So from the projected line, we measure our deflection angle to the right towards line BC, this one. So our extended line is that dotted line, so we measured our deflection angle from that to line BC. So since the deflection moves clockwise, we can say that this is a positive deflection. So for the other example, we can say that this is a negative deflection since the projected line comes from the right, so it means it moves counterclockwise. So our deflection angle here is determined by measuring the angle from the line projected by line CB towards line AB. And please note that deflection angles will always be less than 180 degrees. So next we have the angles to the right. So angles to the right are measured clockwise from the preceding line to the succeeding line. So from the name itself, angles to the right, meaning it is an angle with a clockwise direction that is between the preceding line and the next line. So for this example, the preceding line is AB and the next line is BC. So angle to the right is the angle from line AB going to line BC. So same thing here, preceding line BC, next line CD. So angle to the right would be from line BC to the next line, which is line CD. Next is bearing. So bearing indicates the direction of line. Bearing angle will always be between 0 degrees and 90 degrees. And bearing will always start on either north or south and will always turn to east or west. Now let's try to look at an example to better illustrate the items mentioned. So let's draw first our north, south, east-west line. So we draw a line from point X to point Y. And this angle here will be our bearing angle, and we will call it angle A. So we will assume that angle A is 49 degrees, 34 minutes, and 19 seconds. Excuse me. The first thing that we need to identify is that our angle is on the north east quadrant. So therefore, our bearing XY would call us north 49 degrees 34 minutes 19 seconds east. So now let's draw another line from point X to point Z. So let's use the same angle value as before. So this will be our angle, our bearing angle, and we will call it angle B. So angle B. So we have angle B 49 degrees 34 minutes and 19 seconds. So this, our second angle here, is on the southwest quadrant. So this southwest quadrant. Therefore, we would call bearing XZ as south 49 degrees 34 minutes 19 seconds west. Forward bearing and back bearing. So forward bearing of a line is observed in the direction in which the survey progresses, while back bearing, on the other hand, is the bearing of the same line that is observed in an opposite direction. And please note that forward and back bearings differs from each other by exactly 180 degrees. Suppose you have this line here. So this is your initial point and this will be your terminal point. So if you connect these 2 points, of course you will have a line. So now, since this is your initial point, we will draw here our north, south, east to west direction, and this will be point A and this one B. So the forward bearing, so this will be point A and this will be point B. So this line will be called as line AB. So the forward bearing for line AB will be from the south branch of the meridian to the line. So this will be our forward bearing. Likewise, if we draw our north, south, east to west line for the point B, this angle here will be our back bearing. So if this angle is beta, this angle here is also beta, because this line here, this north-south line here for point A and this north-south line for point B is parallel to each other. So therefore, if you cross the line, whatever the angle here is also the same or is equal to this angle. So this represents as the back bearing of angle of line AB, and this represents as the forward bearing of line AB. So the angle in this point is just the same to this angle. So if this angle is 30, then this angle is also 30. If this is 45, then this is also 45. The only difference is their direction. So forward and back bearing differs from each other's direction. So here we have this bearing angle here. We have the north and the east quadrant. So therefore, our forward bearing for line AB is on the northeast quadrant. And as for our back bearing of line AB, we have the south and the west. So of course, we have the back bearing in our southwest quadrant. So in other words, if you want to determine the back bearing from the forward bearing, or you want to determine the forward bearing from back bearing, you just have to change its direction. So from north to south, south to north. Likewise for east to west, you just have to change the east to west or west to east. So for example, we are to find the back bearing or the forward bearing of north 46 degrees 39 minutes east, north 36 degrees 26 minutes 14 seconds west, and south 57 degrees 32 minutes west. So what is the back bearing or the forward bearing of this given example? So how do we get those bearings? So simple, we just have to follow this illustration. So we have here north, so north change to south, so this will be south 46 degrees 39 minutes, and since we have east here, we will change it to west, so this will be west. Same thing here, so south we have 36 degrees 26 minutes 14 seconds west. So this will become east since we have west here. So there is no need to change the value or the bearing angle, so just change the quadrantal direction. So of course this one will be north 57 degrees 32 minutes east. So that is the way on how to derive the back bearing from forward bearing, or likewise, if you need to know the forward bearing from back bearing, you just have to do the same thing. So you just have to change its quadrantal direction. Next is azimuth. So azimuth always starts at north or south and turns clockwise. So it is the line measured in a clockwise direction from the north or south branch of the meridian. The angles in azimuth will always be between 0 and 360 degrees. And azimuth of a line is its direction as given by the angle between the meridian. So for example, let's draw first our north, south, east, west lines. So this will be north, south, east, and west line. So we have here point A and point B. Point A, B. So we will just align these two, and our azimuth will start from the south branch of the meridian going to this line. So this angle here will be given, and this will be named as angle Z. So angle Z, so we will assume that angle Z will is equals to 48 degrees 23 minutes and 15 seconds. So for this example, we are to find the total azimuth, so this one. Since this angle here, this one, is already given, all we have to do is find this angle right here and then add them both to get our total azimuth. So since this is one quadrant, so this will be 90 degrees, and this also is a one quadrant, so this will be also 90 degrees. So 90 plus 90, we have 180 degrees. So for our total azimuth, this will be 48 degrees 23 minutes 15 seconds plus 180 degrees, and this will give us 228 degrees 23 minutes 15 seconds, and this will be our total azimuth. Forward and back azimuth. So we have here set of rules that are used to determine the back azimuth when the forward azimuth is present or known. So first, we have the first rule, which tells us that if the forward azimuth of line is greater than 180 degrees, we just have to subtract 180 degrees to obtain the back azimuth. The next rule, on the other hand, tells us that if the forward azimuth of the line is less than 180 degrees, then we need to add 180 degrees instead of subtracting it to determine the back azimuth. And please note that forward and back azimuth differs from each other by exactly 180 degrees. So to better explain the rules that I have mentioned earlier, we will illustrate on how to get the back azimuth if the forward azimuth is known or present. So we have our initial point here and our terminal point here. So our line progresses from this point to this point. So this will be our initial point and this will be our terminal point. So for our initial point, we will draw our north, south, east, west lines and our azimuth. So our azimuth will start on the south branch of the meridian. So from this point to this line. Excuse me. And since this is our initial point, this azimuth here will be our forward azimuth. So we have forward azimuth. And so for our terminal point, we will draw our north, south, east, west line, and our azimuth will start from the south branch of the meridian to this line. And since this is our terminal point, this azimuth here will be our back azimuth. We have back azimuth. So as you can see that this meridian line, this south or north-south line of point A and point B are parallel to each other. So it means that this angle right here is also the same with the angle here. So they are the same. And we have this straight angle. So this means that the forward and the back azimuth differs from each other by exactly 180 degrees. So why 180 degrees? Because we have here two quadrants. So one quadrant is 90 degrees. So 90 degrees. We have two. So 90 plus 90, we have 180 degrees. So take note that, go on, that forward and back azimuth differs from each other by exactly 180 degrees. So next is, let's try to make another illustration. So for this illustration, our initial point will be here and our terminal point will be here. So let's just connect these 2 points. So for the progress of our line here, the direction is from this point to this point. So it is the opposite direction of our first illustration. So let's draw our north, south, east, west line in our point A, and our azimuth for this point is from this south branch of the meridian to this line. And for our terminal point, let's draw again our north, south, east, west line, and our azimuth for this point is from the south branch of the meridian to this line. So since this is now our initial point, this azimuth here will be our forward azimuth, and this one here is our terminal, so of course this will be our back azimuth. So here we have two situations. So this illustration here will be case 1, and this one will be case 2. Now our case 1 falls in our first rule. So in our first rule, it says that forward azimuth is greater than or could be equal to 180 degrees. So to obtain the back azimuth, we have to subtract 180 to the forward azimuth. So our formula will look like this. So back azimuth is equal to forward azimuth minus 180 degrees. So this will be our formula for our rule number 1. And for this illustration, so it falls to our rule number 2, where forward azimuth is lesser than 180 degrees. So in order to get our back azimuth in our case 2, we need to add 180 degrees to our forward azimuth. So the formula will look like this. Back azimuth is equal to forward azimuth plus 180 degrees. So this will be our formula for our rule number 2. So for example, excuse me. we have 45 degrees, 229 degrees, and 190 degrees, 58 minutes. So for this example, we are to find the back azimuth using these angles. So first we have 45 degrees. So since 45 degrees or is lesser than 180 degrees. So in order to get our back azimuth, we need to add 180 degrees. So we will be using this formula. So summation 45 plus 180 degrees, this will give us 225 degrees. So this will be the back azimuth of 45 degrees. So next we have 229. So 229, since this angle is greater than 180 degrees, we need to subtract 180 degrees to get our back azimuth. So we will be using the formula for our case 1. So 229 degrees minus 180 degrees, this will give us 49 degrees. So this will be the back azimuth of 229 degrees. And lastly, we have 119 degrees, 58 minutes. So since this is lesser than 180 degrees, we will follow the formula for our case 2. So 119 degrees, 58 seconds plus 180 degrees, and this will give us 299 degrees, 58 minutes. So this will be our back bearing 299 degrees, 58 minutes for our angle 119 degrees and 15 minutes. So that's all about forward and back bearing azimuth.